Hello, my name is Paul Mezebov, and I'm going to demonstrate the use of the Model 7852 and its ReadyFlow software package. As you can see here, I have a 7852 installed in a PCI Express slot in this rack mount server PC. It's an ordinary PC motherboard with looks like 6 PCI Express slots. What I have going into, the signal going into the 7852 is going into the first ADC channel, and it's being generated by a complex signal generator that I have over here. And this signal generator has been programmed to generate a complex wideband waveform. This waveform includes 4 bands of 5 megahertz wide, spaced at 10 megahertz intervals of a complex waveform, centered at 70 megahertz. So if I set the frequency to 70 megahertz, that's the center. The span of frequencies is 50 megahertz. And you can see that we have these 4 bands starting at 55 megahertz, ending at about 85 megahertz. So it's 70 plus or minus 20. And they differ in amplitude by 10 dB. And I did this so that when we down convert them with 4 separate DDC channels, we will be able to identify that the DDCs are tuned to different portions of this roughly 50 megahertz span of signal frequency. Now I'm going to go and show you the software. ReadyFlow software comes with several examples. The example that I chose is DDC4 ACQ, and this allows you to program multiple channels per bank and multiple banks. I've set this up so that we have, at least for this demonstration, 1 active bank and 4 channels per bank. And I've modified the decimation to be 16. What that means is that each DDC is sampling at 200 megahertz divided by 16, because 200 megahertz is the ADC clock. That means that the DDC bandwidth per channel is 12.5 million complex samples per second. And that is sufficient, of course, to represent a 10 megahertz band per DDC channel. Since I have 4 DDC channels, each one giving me 12.5 million complex samples, and a complex sample is comprised of 16-bit I and 16-bit Q, that means that each DDC is providing us with 50 megabytes per second of data. Therefore, in this example, we will data transfer 200 megabyte per second of data across the PC backplane into the PC's memory. I have tuned the beginning channel frequency to 55 megahertz. And I have added a line that increments through the 4 channels that we have programmed by 10 megahertz per channel. That means that I have 4 DDCs. The first one is tuned to 55 megahertz. The second one is tuned to 65 megahertz. The third one is tuned to 75 megahertz. And the fourth one is tuned to 85 megahertz. And you could see on our spectrum analyzer here that that's appropriate for the center of each one of these portions of the signal spectrum. For example, if I say frequency 55 megahertz, frequency 55 megahertz, okay, let's try that again. Frequency 55 megahertz, kept pressing the gigahertz button, that corresponds to the first frequency. If I go to 65 megahertz, it's the second frequency. If I go to 75 megahertz, it's the third frequency. And finally, 85 megahertz is the fourth frequency. Now, we'll center it at 70 megahertz just for fun. Not that this matters, this is just a display. we will execute. First, we can rebuild the application, and then we will execute from within Microsoft Visual Studio. And what we see is that the board is discovered by the application. It's initialized. The threads associated with the DMA transfer are started, and the data is saved to a file. The file, by the way, is named, and this is all part of the standard ReadyFlow package, DDC4 ACQ, and depending on what bank it is, it would be 1, 2, 3, or 4. We have one active bank right now, so it'll be DDC4 ACQ1. Now, I have written a MATLAB script. It's a very simple MATLAB script. It opens the file. It reads all of the data as 16-bit integers into an array called all channels. And then because the data is interleaved in the file in both channel and IQ sequence, I have to demultiplex the data. So I read in 16-bit increments, first an I, then a Q, then an I, then a Q, and I produce a complex vector, as you can see the way that this is working. And then I decide that I will demultiplex the channels from that complex vector. So I read, again, a single channel that I will call A, starting from 1, into this array, and I include, of course, all the samples from each one, and I plot all 4. I take an FFT and plot all 4 of these channels. Let's see what happens when I run this script. Now, what you see is what looks like the same signal, but in fact, if you look closely, you will see that this one is at minus 10 dB, this one is at minus 20, this one is at minus 30, and this one is at minus 40, and it's almost in the noise. There isn't very much signal amplitude in the actual signal. And you could see that the entire range of the signal shows you about 4 boxes here. We know that the top of this is about 5 megahertz. 4 boxes out of 10 would therefore correspond to 5 divided by 0.4, giving you 12.5 megahertz complex sample from here to here. And that's, of course, the bandwidth of the digital filter in the DDC. So this shows the operation of the 7852 down converting 4 bands, 4 wide bands of a single signal and displaying them and being able to move the data, in this example, at 200 megabytes per second with no loss of data.